Now I'm going to take optoelectronic devices, right? Which one? Optoelectronic devices. So we know that electronic devices, right? But today we are going to discuss about optoelectronic devices. Okay students, yes, shall we go to the topic? Right. First one, what is optoelectronics and the major optoelectronic devices and current trend on optoelectronic devices. So we are going discussing these topics, right? We are going to discuss about this topic, right? Okay. Now first, what is mean by or meaning of optoelectronics, right? Okay. Yes, see the first point. Optoelectronics is the study and application of electronic devices that interact with light. So that interact with the light. So electronics combined with optics, right? Electronics combined with the optics. See the electronics and optics, so both are combined, you will get optoelectronics. So in optics, light or photons interact with the electronic segment, that is optoelectronics, right? Okay. Now devices, optoelectronic devices. See, these are the important devices, right? See, the first one is telecommunication laser, is used in telecommunication side, and the next one is blue laser, right? So this is the blue laser. And third one is optical fiber used in telecommunication, and right, and data cables. Now come to this one, LED. So it's used in light, that is traffic signals. And the next one is photodiodes, and the last one is solar cell. So these are the major devices. Okay students, right? Except that some interaction between the electronics, that is electrons and photons. So they were devices same way. The devices are light emitting diodes, laser diodes, photodiodes, and the solar cells. So these are the interact with the electrons and the photons. Okay students, right? So trends in optoelectronics devices. So trends, okay. See the first point, long wavelength high power light sources or photodetectors. It has long wavelength high power light sources, and the user is a photodetectors, right? At the same time, this device is used in nanoscale system, that is nanoscale devices, and this, okay. And low cost easily fabricated material, low cost easily fabricated materials, and it has high optoelectronic conversion efficiency. So it has high efficiency, right? At the same time, multi wavelength sources. So the wavelength is not same, it has different wavelength, that's why multi wavelength sources. Okay students, right? Okay. Yes. Now we are going to discuss about first device, that is LED, light emitting diode, light emitting diode. Okay. Yes. Light emitting diode, see this LED. So one side positive, another side is negative and positive. So this is that LED. So red color, green color, and blue color LED. Yes. So what is LED? Nowadays we are all using LED systems, right? So first, what is LED? LED is a semiconductor diode that emits incoherent yes, that emits incoherent narrow spectrum light, right, when electrically biased in forward direction of the PN junction, forward biased of the PN junction. So it is a diode, so it is worked under which condition? Forward bias condition. Yes, right. So LED is a semiconductor device. Which device? Semiconductor device, right? Okay, right. Next, photon emission in that semiconductor. See, if you are consider material, PN junction, valence band and conduction band. Yes, there is a gap between the conduction band and valence band is the energy gap. So see this, when photon, yes, from higher band to lower band, electron jump from one band to another band, so it emits the energy, so that's nothing but photon of energy, right? So that's why when an electron meets a hole, it falls into lower energy level and release energy in the form of photon. So the wavelength of the light depend on the band gap of the semiconductor material. So for making LED, we used some semiconductor materials. The materials are, see this, silicon, germanium, gallium arsenide, indium gallium arsenide, yes, aluminum gallium arsenide, indium phosphorus, silicon, germanium, and etc. Right? So these are the most using materials. Which materials? Semiconductor materials. Okay, students, right. Again, what is a diode? Simple explanation. See this, a semiconductor device with two terminals, typically allowing to flow of current in one direction, allowing the flow of current in one direction, right? At the same time, see this, light emitting diode. LA is nothing but light emitting diode, is a two LED semiconductor light source, to LED semiconductor light source. It is a PN junction diode. It is nothing but PN junction diode, right? Okay, which emits light when activated, which emits light when activated, when a suitable voltage is applied to the, yes, leads, right, and electrons are able to recombine with electrons holes within the device, so releasing energy in the form of photon. So the light is nothing but photon. The lights come from the LED light is nothing but what? Photon, or photon of energy. Okay, students, right? Okay, next come to the construction of LED. So see this, the LED has two terminals, that is two rods. One is cathode, that is negative, near the, yes, flat spot. So this is the flat spot. Near this flat spot there is a terminal, that is a negative terminal. Yes, the another terminal is positive, right? Okay, now come to the parts first. See, this part is lens. The top of the LED is lens, right? It is a fiber, it is made up of fiber, right? And next, inside that, see this, there is a wire bond connected, yes, connected the two parts. Okay, and reflective cavity. So there is a small, is a concave shape part present here, that is called as reflective cavity. Next, semiconductor die. Here also semiconductor die. Okay, and these two are lead frame. These two are lead, is made up of lead, so lead frame, right? So this is the, these are the parts of LED. Okay, now come to this one, The LED consists of a chip of a semiconductor material doped with impurities to create PN junction. Doped with impurities to create PN junction, right? And the chips are mounted in reflecting ray order to increase the light output. Okay. Now the contacts are made on the cathode side by means of conductive adhesive, and on the anode side via gold wire to the lead frame. So this is the what? So this is the gold wire bond to the lead frame. So this is one lead frame and this is the another lead frame. Okay, and the plastic case encloses the chip area of the lead frame. So this is the plastic frame. So this is the entire is nothing but plastic frame. Okay students, right? So this is the flat spot. Near the flat spot there is a terminal, lead terminal, that is the cathode. So that is negative. Another one is positive. Okay students, right? So semiconductor device, no, the LED is not semiconductor device. So definitely it has P type and N type. Yes, see, this is the materials: silicon, aluminum, gallium arsenide, right? Indium, antimony, yes, okay, tin. These are the materials, right? Now come to this N type. See this arsenic, silicon, right? See the N type semiconductor diode. This type of semiconductor is obtained when a pentavalent material like arsenic is added to the pure silicon crystal. See, arsenic is added to the silicon, right? Okay, each arsenic atom forms covalent bond with the surrounding 4 germanium atoms with the help of 4 its 5 electrons. So here I am taking silicon, so the 4 valence covalent bonds silicon atom, right, with the help of 4 5 electrons. The fifth electrons in superfluous and is loosely bound to the arsenic atom. See, this is the extra atom. See, this brown color is an extra atom. Okay, now come to the P type material. See, this silicon and this is boron, right? So the boron is added to silicon material. So in this type of semiconductor is obtained when trivalent material like boron is added to pure silicon crystal. The 3 valence electrons of boron atom forms covalent bonds with 4 surrounding silicon atom, but one bond is left incomplete and gives rise to the hole. See this time, so here one place is empty, that is hole. That hole is nothing but electron hole, right? Okay, now the boron, which is called an acceptor impurity, causes a many positive holes in the silicon crystal, as there are boron atoms, thereby producing a P type. Producing what? P type. So in N type, P type, both are combined, that is the diode, right? Okay students, right? Now working. See this P type having holes, N type having electrons, and the potential is applied. See, when the positive terminal is connected to P type, negative terminal connected to N type. So what will takes place? Electrons holes across the junction, recombining process. So this is which condition? Forward bias condition. Which condition? Forward bias condition, right? Okay, now see this. When the negative ends of a circuit is hooked up to the N-type layer and the positive end is hooked up with the P-type layer, then electrons and holes start moving, right? If you try to turn or if you try to run current the other way with the p-type side connected to the negative end of the circuit, the n-type side is connected to the positive end, the current will not flow because in that time reverse condition process take place. That time the diode under reverse bias condition, that's why there is no current flow inside the diode. Okay, now see this, no current flow across the junction because the holes and the electrons are each moving in wrong directions, right? Because if you are apply the voltage in opposite direction, there is no current. Okay students, right? How it's work basically, right? See, this is which side? N side, and this is which side? P side, right? See, electrons moving like this and the holes are moving like this. So when current flows across the diode, the negative electrons move one way and the positive holes move other way. See this, electrons move one way, right? And the positive holes move other way. Okay, right? Now the holes exit at a lower energy level than the free electrons. Therefore, when the free electrons falls, it loses energy. See, this is free electron falls and its losses energy, right? Okay, now the same one, when the fall loses the energy, this energy is emitted in the form of photon which causes light. Okay, see this, the color of the light is determined by the fall of the electron and hence energy level of the photon. See this, so it emits photon. So this is the what? Photon, right? This is the what? Photon. Okay, right? So this is the working. See this, p-type, n-type connected in forward bias condition, right? This p positive is connected to p-type, that's why forward condition, right? Now see this, electrons here holes. Now the conduction band, this is the valence band, right? Now come to this one, a particular voltage, the electron jump from free electron jump from conduction band to the which band? Valence band. That time, yes, it loses the energy, that energy in the form of light, the form of light. Okay, okay students, right? Okay, next, types of LED. Nowadays we are all using different types of LED now. See this, so these are all LEDs. Yes, these are all LED, different types of LED. So LEDs are produced in variety of shapes and sizes. The color of the plastic lenses is often the same as the actual color of the light emitted. See, yellow color, white color, red color, light green color, yes, and the white color. So these are all LEDs, types of LED. Yes, variety, shapes and size. Okay, right? Okay, now types of LED basically nowadays. First one, traditional inorganic LEDs are using in different manner, right, and different circuits. And multicolor LED, in multicolor LED classified into two types, one is bicolor and tricolor, right? That is dual color and multicolor, that is tricolor. Okay, the next one is organic LED and is miniature and high power. So these are the what types of LED. High power LEDs, last one is high power LED, right? Okay, first one is multicolor LED, that is first one is bicolor, right? See this, multicolor LED. Two different LED emitters in one case. Two different types of LED in one case. So there are two types of this. One type consists of two dyes connected in the same two color types of light. Another one is current flow in one direction emits one color, and the current in the opposite direction emit another color, right? So these are the bicolor. Bi means two colors, right? Two color LED. Okay, see this bicolor LED system, right? Okay, right. Next, organic LED, that is OLED, organic light emitting diode. So this OLED mostly used display technology, computer monitors, and even used television and mobile phone screens, etc. Right? So these organic LEDs is nothing but mobile phone screens, that is OLED. Right? Okay, right. The semiconductor in an OLED is organic, which means contains carbon. So this is the structure of OLED. The OLED used once two polymers or small molecules. Yes, so polymers we are used here, right? Okay, that is OLED. Next, high power LED. For example, in this picture, this is the high power LED. This LED emits high power. So for example, Grease XP series LED achieved 1.105 yes watts in 2009, which is Nicrea released in 19 series with a typical efficiency of 140 illumination per voltages in 2010. So this is the high power LED which emits high power. Okay, right? Okay. Now comparison to the LED light and a normal CFL and halogen bulbs. Right, LED, CFL and halogen bulb. The life is, see this, 25,000 hours, but if you go to CFL, 10,000 hours, and if you go to halogen, 1,000 hours. And if you go to the watts, 7 watts, CFL 13 watts, and halogen 43 watts. And cost per bulb in dollars, $11, CFL $4, halogen $1. And kilowatt hour used covers 25,000. For example, 175 kilowatts per hour, CFL 325 kilowatts hour, and halogen 1, yes, that is 1075. But bulbs needed for 25,000 hours, ordinary bulbs, one bulb is enough. Here 2.5 bulb is enough, and halogen bulb 25 bulbs is enough for 25,000 hours. And 25,000 kilowatts hour, if you used 25,000 kilowatts hour used, what is the cost in dollars? So LED around $21, CFL $39, and halogen $129. So total cost of 25,000 hours if we use LED light, so the total cost is $32.95 for CFL, $51.45, and halogen bulb $178.50. Okay, right. Applications of LED. So LED use fall into three main categories. It is used indicators, used as signal lights, and is used as a lightning devices, and used in data communication, other signaling process. Okay, so these are the major categories, right? And now applications. Other than that applications, these are the main applications. See this: sensor application, mobile applications, sign applications, LED signals, illuminations, indicators, right? Now first, sensor application. See the sensor application in the sensor application, that is LED is used in medical instrumentations and barcode readers and color and money sensors, encoders, optical switches, fiber optic communication systems, right? And then next, mobile applications. So it is used in mobile phones, in PTAs and digital cameras, laptops and general backlighting. Yes, so mostly general backlighting nowadays we are using LEDs. Okay students, right? Okay, and now yes, these are the optoelectronics and which one, LED, light emitting diode working functions. Okay students, right? Okay students, today we covered two topics, that is optoelectronics and LED. Okay students, right? The same time on Wednesday you have test. For that test the portion is 10th lesson. So in 10th lesson 3 marks, 2 marks and 5 marks. You have to study the 3 marks, 2 marks and 5 marks. Okay students, right? Okay students, yes, today class is over. See you on next class. Okay students, thank you and thank you for your attention. Thank you.